Oh, by the way, like I still like to not exactly a correction, but I guess I stumble a little bit like for the weight initialization when you have a value layer. So I guess let me okay. If you remember, like okay, you want to initialize the weight such that like when you go through the layer, the variance before going through the layers and the variance after going through the layer is still the same. So then we say like if we have a value layer, basically what we're doing is, let's see, I change to web. We are going to let's see, we sum every, okay, we have weighted sum with some input x here, so weighted sum here, let's say x here, and then afterward, then we are going to go for a value layer, and here we call it y here, so this is the L layer, let's say, this is YL here, so before that we have another value layer, so therefore like this guy is YL minus 1 here, let's say. And so when we compute the variance of YL, so we very simple, we go through last time like that. And then we say, okay, this variance, this multiply W with X, can be expanded like this. And we say that, okay, because W have zero mean, so this is gone. So we still have this guy. When this added with that, then we have this. So we need to be careful with the notation. Again, this is expectation X squared inside the expectation. And this one is like outside the expectation. And then I guess I stumble a little bit here. So this is equal to what we have here. Should be careful. Like this expectation X. Oops, that's the thing. Like this will be gone. Let's see if I can. Yeah, this thing here. So this expectation. That's bad. This square thing here, will be okay, yeah. So this one here, let me draw again. Draw it here is better. So we have XL here. So this have a value layer, and that's a YL here, YL minus 1 here. So I was stumbling a little bit because I was confused that I'm thinking this would be a bad approximation if y is not zero mean, right? If y is zero mean, it's okay. If y is zero mean, then half of the energy will be just gone, right? Because y is zero mean, you have half of the time is bigger than 0, then it will still be equal to that original value. But when it's half of the time when it's less than 0, then it will be like kind of chopped to 0, like when passing through this value layer. So therefore, like the energy for YL, if y is zero mean, then should be double of this energy of this XL, or like the expectation of YL minus 1 square should be should be 2 times, right, of the expectation of XL square, or the opposite will be expectation XL square will be 1/2 this expectation YL minus 1 square. And if YL is zero mean, then this expectation will be just equal to variance, right? So because if your variance, let's say W, will be just equal to expectation W square minus expectation W square, right? So if it's zero mean, if that variable is zero mean, then these two values will be the same, right? So therefore this will be just equal to variance of YL minus 1. Something like that. So therefore this will be equal to that, but it's all condition under the condition that YL minus 1 should be zero mean. So but why this guy should be zero mean? So know that this guy here is equal to W multiplied by, I mean this sum here, right, is equal to W, actually L minus 1, XL minus 1, this guy here. So if I compute the expectation of Y here, will be expectation of this guy here. So that was when I was a little bit confused, like, okay, is that really zero mean? But it's okay because X is not zero mean, but W is zero mean, right? So therefore, like, you will, if you assume that these are uncorrelated again, then you have like expectation like Wi multiplied by expectation Xi here and sum over I here. So Wi is zero mean, so this is zero, so therefore like this guy is zero mean. So that, I mean, this, that's still like approximation here because we need to make sure this guy are uncorrelated, but it's a very reasonable assumption. So last time I stumbled a little bit. Yeah.
There will always be a bias term added.
Yes, but the bias term you assume is also zero mean also. Because it started as zero mean, yeah. So when you, yeah. So, yeah, and that's what I want to kind of correct. Even though I don't think I'm too incorrect last time, but yeah, I don't think I articulated very well. So let's go to what we like to talk about today. So let's continue what we ended. I guess we ended where? Oh, yes. Basically, we ended, yeah, just we only talk about weight initialization last time. We talk about weight initialization, and we talk about some activation function. And this time, let's start with like batch normalization. This is something like also a very kind of important technique to help you to better train your neural network. So the idea is like under some layer, for example, if you have let's say you before some kind of 10H layer or something like that, you may want to, in some cases, you may want to make sure that like your input is not saturated, in the sense that you want to have the input is like in certain range, right? You don't want it to be too big or too small. So in that case, actually one trick we may do is simply p-normalize what we are getting into the input. More precisely, let's say we always kind of train the data. I mean, train your network a batch at a time, right? So what we can do is we take the batch and we kind of like normalize the data such that the mean and okay, it would be zero mean, so we subtract the batch mean there, so we compute the mean of the batch. So we subtract that, and at the same time we can kind of normalize with the variance of the batch mean. The variance of the batch data. So in that case, this guy will be univariance, right? The data you're getting into this input will be univariance. And of course you will say like whether it's a good idea to be univariance, but yeah, you can do that. And actually, so just as the last slide, simply it's a very simple idea: compute the empirical mean and empirical variance, then normalize it. And then like we can insert this batch normalization, like for example, before like this activation layer like 10H, you expect that like you don't want to get to the saturated region, so you want to scale it back. And and you can insert it anywhere basically, but you can ask like, okay, is that really a good idea? Because sometimes maybe I really want it to get saturated. So then one more thing we may do is we can kind of what's the word for that? So you can like after the normalization, you can stretch your variable back in the sense that you may scale it back and kind of like add back a bias factor, and let this scale factor and also this bias to be some other parameters. So in the sense that, okay, you have this normalization step, like batch normalization step, immediately you can also like introduce 2 more parameters there, and these parameters can be changed by the lateral also. So therefore, like if you under some situation, let's say you are not supposed to scale it back, then you can, your network, your data, supposedly will automatically train this parameter such that this will inverse this operation here. So therefore, like in any case, like basically you don't lose. You add this layer here, and you it's always some gain there almost. So therefore, it's a very powerful technique here. So again, like to summarize here, we just simply compute the batch mean and batch variance, and then normalize, and then scale and shift, and then these parameters we are going to train again. So and any question for that? So it's a pretty kind of intuitive technique, but it's really pretty powerful. So yeah, and of course at test time, then you will just use that parameters that you train this scale factor and this bias for your training. Okay, so we have some other techniques to kind of if you remember, like we keep on emphasizing is that like it's important to reduce the training error. That's how, I mean, the only thing we can do, like, because that's the training data we have. We have this objective function. Okay, we just want to minimize the training error, but by the end of the day, really the testing error is important. So one thing that really we want to see, like how we can make sure that the gap between the training and testing won't, I mean, in a reasonable size there. You expect the training error will be bigger, but at the same time, like you hope that like it won't be much bigger than the testing. Oh, sorry. Yeah, I mean, yeah, the test, yeah, or the validation error there. So there's some trick to do that. One very simple trick like to emphasize is simply we call it an ensemble trick. Just think of that you have multiple models. So you have, let's say you have a neural network there, you have a SVD there, you have some naive Bayes, any model there, and then like you just train these multiple models, and at test time you just get all of the results and do some weighted sum, do some averaging, and typically you will get some extra like 2% performance there. So you always gain like doing some simple stuff like that. And we can extend this idea into different variation. Sometimes we don't even need to have like completely different models. So one possible scenario is that like, okay, we just have one model and we train it like train it, right? But we can stop at different track points there. At different track points we'll have different parameters, right? Different train parameters. And we can consider all these parameters are different models. And we can actually do averaging over these track points there. And yes, you need to, I can't hear you. Yes. No, press that. Yes, now I can hear you actually.
Does that trick work every time? I mean, for a single model, combine the output at different checkpoints.
So you, is your question that like, do we train it every time?
I mean, does that trick work every time?
I mean, this trick does it work every time? Do you mean like?
Yeah. Yeah.
That I can't promise that, but I think like it works most of the time. So it's definitely. And also an important point is like you don't really pay extra. Almost you don't pay extra for that, right? Because when you keep training that, like you always have those track points. Like, you just store these track points, and then you do the averaging. And of course, like up at the end of the day, you look at the last result and the average result. If this average model does not work better than your last model, then you just forget about it. But basically, you didn't really do much extra work for that. Yeah. But I guess according to this paper, at least they claim that like you can almost always get better. Yeah. So yes.
How many models that should be averaging on that?
I guess it's up to you. For example, in this example here, you just do 6. So, let's see. I'm thinking like whether this is the. Okay, I think this one. Let's see if I remember correctly. Okay, I think what they did is like, okay, they train it up to here, then they restart in the sense like they change the learning rate back to something big, and then do it again. Like here, the learning rate actually like go down a little bit. So, and then like at this point here, they consider one model here, and then when they go back up, use a new bigger learning rate and continue to train again, go down. And then they at the end they consider a second model. In this case, they just have 6 model here, and there's yeah, that's I guess like that's they are comparing with like let's say they are just using one learning rate and going down like this. This probably is not better. It's not as good as like if I train going down and then up to a certain point I say, okay, let's restart again. Let's make the learning rate big again, and then continue to train, and the learning rate slowly going down, and do it like several times, and that actually may give you even better result. So you may want to take a look of this paper also. Like it's really recent also. It's like 2017. Yeah. So I may not be correct honestly, but so okay. So this is like some very simple trick, and yeah, that's basically actually the original one. They also call it like Poyak averaging sometimes. So okay, the next trick I like to talk about that is also like used often, very often. Is like the so-called dropout. Actually, it's so popular that like it's almost standard also. So the idea is like it's very simple. Basically, you have a neural network here. So as like here. So what you're going to do is like during training, I just randomly drop some outputs, intermediate outputs. So drop meaning that I just set it to 0, assuming nothing happened. And then like each time I just train like this. And then at the end, like I will combine these weights like kind of like intelligently, as I will discuss later on. So of course, it sounds like kind of crazy. It doesn't seem like this would be a good idea. So, but in terms of implementation, as you can see, it's very simple. Like, basically, you just generate a random mask somewhere. So, for example, like, I will drop out like P fashion of the nodes there, like node output there. So then I just create a mask there. So when I drop, I will just like do a kind of like element-wise product with that mask. So, and one argument that why this actually work is that like you may consider this as some kind of regularization, in the sense that like you remember regularization is basically trying to pull back your weight a little bit, not to go completely crazy. And so here, what you can imagine is like, for example, in some intermediate layer, you may have each of the nodes correspond to different characteristics of the object you're trying to recognize. For example, a kind of a simplified example that we have, let's say we're trying to recognize a cat, and let's say in the intermediate layer here, we have some of the nodes correspond to like different characteristics of the cat, like whether it has a tail, has a ear, and so on and so forth, And then, so when you drop out some of the intermediate output there, basically what you are doing is, it's basically we kind of like forced to have some redundant representation, right? Because we are not relying on, for example, like it may up to a certain point that, okay, I think the cat must has a tail because like all my data has a tail or something like that. And I may overemphasize this particular feature there. But then maybe because you have because maybe in your data you only have cat and human and monkey. And then to monkey, okay, monkey has tail, I'm sorry about that. And cat and human, something like that. And so therefore like what you have is maybe therefore like you overemphasize this like has a tail factor there. So then this weight here maybe like it just going crazy here. Like you have to this weight here trying to really emphasize this guy here. So the dropout essentially what it does will be like randomly, like occasionally I will de-emphasize some of the features, right? So occasionally I will say, oh, you cannot consider that this has a tail as a feature. Then you will force the other guys to, you look at other features also, so you will get the weight more spread out. So it's kind of like a hand-waving argument, but there's some truth there also. So another way to look at that is like, you can think of like dropout is really just an ensemble trick go to the extreme. So in the sense that like you can think of each time you have a different ensemble really, or like each time you have a different model, because like when you cancel some of that node, like you kind of disable some of the nodes, you essentially have like a different network, right? So therefore, like you're actually using a different network each time to change the model. But of course, like in this case, when you train this one network, you only use one data point essentially, one data input. So therefore, that's why I said that it's really pushed to the extreme case. And of course, like, actually, there are many models here if you count that. For example, like, if you think of like one fully connected layer with just 4,000 units there, so there will, just in that particular layer, you will have like 10 to 1,000 possible masks. So it's much more than the number of atoms in the universe. And so basically, you have so many models, you will never get exhausted. So that's my point here. And as I mentioned, like at the test time, you cannot simply combine this model like blindly. Actually, the best scenarios will be you think of like each time here I have a set here or Z here is basically trying to represent like I have different kind of dropout here, like dropout different nodes here. So and now the reasonable kind of way to combine these models, you think of like maybe I should just average them out, right? So we'll be doing something like integral or like a averaging over all this model, right? But the problem is like that will involve lots of computations and not efficient. So in practice, like we usually just we do not do the average. We simply assume that like okay, because we train it, we have all these different weights, right? Or each time, or what should I say? If you think of that, this is not even possible. If I try to do this way, that means that like each time after I train it, I should save the weight of this model, right? But then I need to save lots of weights there because each time I train, basically it will have like the number of models will be proportional to the size of the data set. That's typically goes to millions or something like that. So that won't be reasonable. So instead, like what we already actually explained, like when in the training, what really doing is it will keep training, right? Because each time I have a different data coming in, I will simply kind of drop out different nodes there that correspond to different models, but I will keep training like this. And by the end of the day, I have the weight is more or less like the average, but I cannot use that blindly because if you compute, let's say, just simply consider a very simple case. Let's say I have two input nodes here and combine with a weight W1 and W2. And let's say I try to compute simply the expectation of A there at test time. So the expectation of A at test time should be will be simply like this, right? It's nothing. Okay, at test time I simply like use W1 and W2, and input is X and Y supposedly. But during training time, remember that like I have all these nodes. Basically each of these will be randomly dropped, right? So therefore there will be like 4 different cases here. Either like both of these are not dropped, then I will have this. So let's say I assume the dropout probability is just 1/2 here. So I will have 1/4 probability for this to happen. And I may have like one of these guy drop where I have like this, maybe this one drop here. I have like 1/4 probability. And I may have like both of them drop, and I may have like the X here get dropped here. So then if you compute that, the average will be actually 1/2 of this one. So therefore, like, in the sense like during testing, you see that like I need to scale it up, to get the original result there. So therefore, like what we should do, we should, not scale up, scale it down. So we should really multiply the dropout probability for the, during testing time. So therefore this will be something like that, like when we're trying to predict the result, let's say this is the weights that we got trained there. So what we are going to do will be simply, multiply that dropped, just scale the activation function back scale it down by the probability there, and that's about it. So any questions here? So on this thing, I'm not sure. Like, okay. So, but actually in practice, I want to mention one more thing, is that because I think of that like, training, you have all this computational power, right? You may have GPUs and so on, but during testing, maybe you want to use the cell phone to recognize something, right? So you want to push the complexity at the test time as small as possible, typically. So sometimes what people do is like some of this called like a inverted dropout, that in the original dropout we scale it, scale at the test time, right? And for the inverted one, we simply not scale it at the test time, but instead like during training time we will scale it. So do the scaling during the training time. So then like we won't add any more computational complexity during testing time. So any questions? So if not, let's see. I want to mention another very simple trick can help you for get your model better. We mentioned like today we mentioned like batch normalization, and we talk about dropout. And one more trick is really easy to do, like even easier than what we discussed earlier, is you have data, right? For example, you are doing like image recognition, you have data you want to recognize as a cat or a dog or something like that. One really simple way to improve your kind of network is simply trying to generate more data. So of course, like, this sounds like what's that word? I forgot. But it doesn't sound like it sounds like if I have more data, of course I can use more data. But what I mean is like, even if like at the beginning, maybe like you only get so many data, you get like 1,000 images, but you can still like do some simple trick to make more data. For example, like think of like, this is a cat here. So you think about, okay, this is a cat. What do you think, like what else you believe this is a cat? If you change the kind of the brightness of the image, for example, perceptually you will still think it's a cat, right? Or like if you flip this image, you make a mirror image of this cat here. For a human being, you will still think that this is a cat, right? Or you may stretch it, like something like whatever, add some noise. So therefore, like we can simply, for example, introduce very simple transform. Let's say if we just flip the image. So immediately we will double the number of images, right? So we can increase the number of data simply like with tricks like that, like 10 times, let's say, easily. So and this is some like for example, do some horizontal flip, and even like for example, like I can just randomly crop this image. For example, like this is a cat, but I think like if I only have this part, I still think it's a cat. And maybe if I only sit this here, maybe I still am able to manage to think it's a cat, and something like that. And then you can get even much more data. And as I mentioned, that you can resize and do different scale, and wait a sec. Yeah, actually, this is what one of the that we are going to talk more later on is a Westlet. What they did basically, they have the image there. For them, they did the data augmentation this way. They kind of like pick random region, like with this range here, and then resize that range there, and and then let's see, pick random L in range. Oh, okay. I think this pick random L. Okay, random L is just like pick different location. Right? Okay. So yeah. So for testing, oh, okay. And also testing, you can do something similar, right? So you know that when you have different models, as we mentioned earlier, if you use the ensemble trick, you can get better result, right? So even you have the same model, you can do something similar. So you can, okay, if I test this image, I can also like shuffle this image a couple of times and put into the same model and try to recognize it and do a majority rule for my result. So maybe, for example, here I can resize this image into different scale, and then like I can also like crop it in different sense, and then like see like whether it will recognize as a cat or a dog, and then just take a majority vote of your result. So it's a very simple trick there. Okay, that's some other example also. You can, besides like scale it, you can do some random jitter also. And basically like you just can think of anything like you can do. Right? You can go really crazy. Like for example, you can even distort the lens here. You think like, okay, you can warp the image a little bit, and for you still think this is a cat, then you can include that in your kind of data augmentation also. And of course, like this depends on your problem. For example, if you apply to audios, maybe you will have different kind of augmentation, but images is just very intuitive, like how you can stretch your data and input and output. You stretch your inputs, and still you think this is what it is. And okay, I'd like to mention a couple other regularization techniques also. It's also similar flavor as this ensemble trick. Also, like you may have some kind of like, you can think of this randomness, or like something like you generate several different models, and at the testing time you just average them somehow. So we mentioned like actually dropout and data augmentation, actually batch normalization, somehow you can still, more or less, you can also like kind of classify in that sense. And another like kind of very similar technique to dropout is so-called drop connect. In that case, it's like you're not dropping the output of the node, but instead you just drop some connection. So it's very similar flavor. There's another one is kind of interesting also, that but actually we didn't describe mass pooling yet. So mass pooling is basically like you have some inputs there. So let's say you have images, you have two-dimensional input. You just like for a particular region, you compute the max and use that as a summary. So, and then like typically you may take the pattern, like let's say you may take a regular pattern, right? So you may have like each block here to have same size, let's say. But you can also go like introduce some different models as before by stretching this pattern like in different sense. For example, I may have patterns like this for this one as one model, and different patterns of different models, and that will give you a and a different kind of regularization. And there's also one different approach is like kind of similar. Is like we can even think of like we have a long big network, and sometimes like we are not even dropping like output, but we drop like whole kind of layers, several layers one time. So we randomly drop some layers completely. So this is pretty new work. I guess like it's 2016, and I guess there's still like lots of ongoing research like on like analysis of this kind of techniques. But as I mentioned, like just along of this flavor, actually you can do lots of varieties. And let's see what I still have some time. So I will talk a little bit about optimization basically. So remember, okay, we mentioned that the optimization we used previously typically is very simple. We just do a gradient descent, right? So we want to find the minimum loss for with respect to the parameters, right? So and we mentioned that that will be some issue. We mentioned, okay, actually we can use momentum. I will kind of review that. I can give a short revision for that. I guess we mentioned one of this example, like why sometimes a gradient descent itself is not sufficient. For example, if you have your function is pretty skewed, that like in one dimension is much steeper. Actually I should point this direction. It's much steeper than the other direction. In that case, actually more technically, that correspond to the Hessian matrix. Correspond to the loss function itself have a high condition number. The condition number is defined to be the largest, the ratio between the largest to the smallest singular value. So it more or less like the ratio between this and that. So, and of course, like, if the conditional number is big, then it means that like you have some of these assets is really kind of much bigger than the other assets. And I want to say, like, emphasize that this is actually pretty common in reality, because remember that like we are always working on a really high dimension, right? We have many parameters, right? So therefore, like we definitely will have one dimension that will have a slope much larger than, let's say, another dimension have a slope is much much steeper. It's, of course, if I am only in 2D, that doesn't look like it will be that. But if we are in high dimension, then you can imagine, like, yeah, it should be quite common. And so, and I guess we mentioned that last time. So if we, under this kind of situation, if we just simply use steepest descent, then we'll likely to get something like this back and forth, like kind of oscillating kind of gradient that will take quite a while to get to the minimum. So there's also like some other problems. So some typical problems, let's say we have local minimum, and then in the sense that if we go steepest descent, we're just stuck here. But sometimes, even though it's not local minimum, if let's say it's just a saddle point there, still like maybe like this slope at this point will be 0, then I will still be, our optimizer will still get stuck here. And one interesting thing like people realized recently is that for high dimensional optimization, saddle point is much more common than local minimum. So it may not be intuitive at the beginning, but it's reasonable, right? Because when you have very high dimension, you will imagine, okay, you have a value here, there's always can find some dimension actually going down, right? So if you are, because there's so many dimensions there, so if this is not really the real local minimum, then there's doomed to be one dimension that like actually will going down somewhere. So therefore, like actually in high dimensional space, typically the function will have like more likely will encounter a saddle point problem like more than a local minimum. But in other case, the momentum, okay, that's one more thing. Like because we are using mini batch for optimization for estimating our gradient, so our loss function is not exact also. So therefore, like this, in reality, it would be something like that, right? Our gradient, even though like it can be like this function is pretty smooth, our gradient still will be like approximation, maybe will be like kind of a random walk going downhill. So, but many of these problems can be solved with this momentum update. I guess that is just a review here. And basically, so if you remember, what we are doing is like, we simply, instead of going down, let's see. let's see if I can. Yeah. Instead of we have x going down to the gradient directly, you have like compute some kind of, let's say, velocity, and that velocity will kind of have actually I would say like inertia is a better word than like a momentum. It will have some kind of inertia such that it will kind of like retain like the previous value there, but it will also be affected by the current gradient. So therefore, like, you have your kind of like your velocity won't change suddenly. So that actually will be helpful for both of these cases, right? Think of if you're going downhill here, then because you have the momentum, then hopefully you have this momentum will be big enough to push you up here, right? Or like if you have just a shadow point, it will be even easier that you don't need to go up, then you can just like, hopefully you have enough force to keep moving and continue to go down. And so this is, and also like, of course, like if you have momentum also, if you have this kind of oscillation here, back and forth, this oscillation go this way and this way will get cancelled, right? So therefore, like, mostly you will still only have this kind of like this component left. So therefore you go more smoothly in this direction. So it's not too smooth, but still. So this is for, I guess, the next simple kind of improvement from stochastic gradient descent. And we can actually have a little bit better momentum update based on something known as a Last-Rove momentum update. Well, actually, this is a pretty old paper in the 80s, but like people rediscovered that like recently. So actually it has some kind of I didn't get into the theory part. It actually has some nice theoretical property that for converse case, for example, at least you will always converge better than the original momentum update. So at high level, it's more or less like this. So you will have instead, if you think of the momentum, basically you have the original kind of previous velocity, and then you compute the current gradient, right? And then like you will just sum that up, and you have the new kind of velocity here. But for the Last-Rove momentum update, basically you will just go one step ahead. You will look ahead, and you will first like have the momentum step there. So you have, assume you move one step ahead, and at that step there, at that new point there, you will compute the gradient. So then your actual update will be like this guy added with this guy. So hopefully I will make it clearer here, like with the equation. So therefore, like basically you see, like I'm computing the gradient not here, but I'm computing the gradient after I have added the previous momentum step there. And then like so the new velocity will be just like the old velocity added like this gradient compute at this point here. So one kind of like con here of using this directly is that it's kind of not very convenient, because you need to compute the gradient at different points. So you need to first move up here and compute the gradient here. So because it's it's just not convenient, I would say. So but we can actually make slight changes. So just use some simple change of variable. Let's say I change the variable with this oops, I'm not sure this is okay. Sorry, actually this is not the slides I'm supposed to use. I don't know whether I have the That's bad. Like sooner or later, there's too many versions. And then just, let's see, I think it's, yeah, I have a little bit better version here. I prefer to use this one. Oh, by the way, like my slides keep changing, so if you downloaded this like a couple weeks ago, you may need to re-download that. Yeah. So let's see if I go back to there. No, I guess no, it's okay. I guess I changed that, and I just somehow I don't know, like I have too many versions. So, but it's okay. So so anyway, we can simply do a change of variable. So we have this kind of like change it to find t-1, then you substitute to this guy here. Then now the new update like will compute gradient at the points that I mean at the point I mean we'll have a form very similar to the previous one. And actually the other slide is this is the slide that also like by CS231N, but it's like the previous year. So the newer one, they have a slightly better slide that like they actually you can also shuffle this, I guess, a little bit, and then you will see that this is actually it's okay. I maybe next time I'll show you again. So anyway, so I will just move on. So and this is with the momentum, and I guess has the energy here. It looks a bit better here. This with the less two of like accelerated gradient, and other approaches I like to mention is like something known as autograph. So the main idea is basically like it's again like pretty simple. Like you it's trying to solve something similar to this. So you have gradient along one direction is much steeper than the other direction, right? One way we can do is simply we can scale the one that is steeper, like by some value, like and this that is not as steep, like basically like each dimension we just scale with different factors, and that's basically the factor here, and that factor will be simply we'll use the previous gradients. So basically we'll sum up the square of all previous gradients and use that as a scaling factors. So please be careful that we have Python notation here. So sometimes I will get confused also because this is element-wise division. So this is a vector here, this is a vector here, is an element-wise direction. So each dimension I kind of scale it. Basically if the gradient at that point is smaller, so then this will be scaled to a smaller unit, right? Smaller size, right? So therefore, like each dimension will be kind of like have similar values. So hopefully you will have a little bit better kind of like more or less like we'll have less oscillation as in original SGD. And but actually actually this is a work, I guess is sometimes 2011 or like 13. I need to check it again. And but people typically don't use this. because the problem here is that as you accumulate this the square of the square of the gradients, so this will get better and better, bigger and bigger, right? So then this automatically have the effect of like decreasing the learning rate. So sometimes it is good, but sometimes you just overdone this. So and you may not want the learning rate to decrease as quick as like this. So and other way, instead what people may do is, okay, we can do something similar as using the similar idea of momentum, right? So we won't use this square of the or like, actually it's not exactly the same as the momentum, but instead of like accumulating all the square magnitude of the gradient, we may just forget it after a long period of time. So we just use the recent one. So that will be like, have something like this way. So basically, we'll kind of like, we'll have like a, kind of, what's that called? AR model, that kind of stuff. Auto-regression. So anyway, but if you look at the formula, it's basically like that, right? We will just keep, yeah, it's okay. The formula is like, I guess it's obvious enough. So any questions otherwise? I guess what it means again, like the original, because like we will accumulate all this square magnitude forever, right? Oh, okay. Yes.
In the the update, the cat is becoming larger and larger.
Actually, the learning rate will be smaller and smaller because it's like, you see, like it's like you get divided by this some way. So basically your learning rate will get smaller and smaller. Sometimes you just get too small. So therefore, instead of doing that, like we'll just not sum everything. We just like use the recent ones, right? So we will just do a averaging. Like, shit, I forgot that word. So then like you use basically like you just use some of the previous one and like weight the sum by like the most recent like square of your gradient, right? So and yes.
So in the ADA grade, every time we use all the grading in the every time.
Yes. For other grade, we use sum of all these gradients in the past, or like the square gradients in the past. Yeah. And here, like we will kind of have a smooth averaging, basically. Like we will, in effect, like basically we'll forget like something is long time ago, only store kind of average over the, yeah, okay, I find the word moving average, right? This is exactly the formula for moving average, right? This remind me, I'm bad in English. Yeah. I'm trying to look for that word. It's so difficult. So anyway, yeah, this is just a moving average, right? So yes, and that's cool. And something like an interesting remark is that like this is not even published. This is like in Jeffrey Hinton's Coursera course. And it's like in some lecture 6, somewhere he mentioned that in one of the slides. Therefore, like when people write papers, sometimes just reference to the Coursera course. So I think it's something kind of unusual, like in, I guess, like in academia. So and that's some also like you have, okay, this is our MS pop. Actually, it's look pretty nice here. And finally, okay, this is the last one I had to mention. Actually, this sounds like a long story. I guess, it's really for the benefit, like for you guys really interested to do some optimization research, like in this particular area. By the end of the day, unfortunately, I wasted you guys like for 25 minutes, or maybe 20 minutes or like something like that, because I most likely will just simply use Atom here. So, this is like the recommended method, like at this moment. Of course, it's good to understand like what is going on, like the history and then like. So, Atom is basically just combining many of these ideas. So you have momentum there, like you have, basically, momentum for your gradient. So you basically do a moving average. Okay, now I have this vocabulary, it's easier. You have the moving average of that gradient, right? So you have this M here. And then you do the same thing, also the moving average of the gradient square. So then you have basically, you update with the gradient with the moving average of the, you go down the slope along with the moving average of the gradient, right? And also it will be scaled by, just like in our MS pop, by the moving average of the gradient square, basically. So this is more or less the atom. So it's not complete. If I want to make it complete, it's basically like this, because if you look at this in the initial step, you will have the original first moment and second moment, like when you initialize this will be equal to 0, right? Then you will kind of overemphasize, and actually I'm not sure emphasize is a good word also. So, basically I just want to have some bias conversion here. So then I will add this term here, just like divided by 1 minus beta 1 to the power t here. So then when t is more, then this basically get cancelled, right? You will have the original dx there. So, and original dx squared there. But as it goes back, then this effect will get smaller and smaller, right? So these terms here will basically disappear. So this will just become this original one here. So therefore, like, we only add this bias correction basically for the initial several steps. This is some of these parameters, like, it's good to use, like, for Atom. And I guess I probably stop here. So, yeah, I guess I will just stop here. So, any question? So, but unfortunately, I wasted 2 hours before this lecture. I changed all these slides here. I don't know why it's gone now. I don't know what I did. But anyway, but I don't think you missed much. So this is the slides I used last year, but I think it's still good enough. Any questions here? So actually, I created a notebook there. I mentioned to some of you guys, like, just before the lecture, I played with that notebook. And I didn't realize that, like, the notebook also automatically generate a PDF file for these guys here. So therefore, I screw up all these images, like, just before the lecture. And, luckily everything is in Dropbox, so I just put it back. But, maybe along the process, I also, like, erased something, so therefore the update was not there. So anyway, like, any questions? If not, then I guess, yes.
Before dropout.
Yes. Dropout. Yeah. or before dropout? Before this one.
Yeah, my question is, the right line and in the right flag figure, in a period we include our value like that. So is that found another high point in the figure, or it's just like relatively high between this checkpoint to another checkpoint?
Can you repeat that? I don't actually get the question.
Just look at the red line.
Yes.
And the red figure. You said this cycle is like 6 cycle.
Oh yes.
And as a checkpoint, do we change another point or just calculate the relatively high between this checkpoint and another checkpoint?
You mean do we calculate what again? Like
So the red line is the checkpoint in the end of the cycle.
yes.
Rise.
Yes.
A lot of highs. So I don't know why. Is that to find another high point, higher point?
Oh, okay. I guess like the main idea is like when you go down, like there's a chance you may stuck in local minimum, something like that. Then when you're stuck, you just get stuck. So what they do, okay, so remember that you have the learning weight there, right? And the learning weight is kind of like the step there, right? So if you are stuck here, so let's say I have like here, like let's say the local minimum here. So I compute gradient somewhere here, let's say, okay, the gradient here, let's say is almost 0, but if my learning weight is small, I will never get out of here, right? If like my learning weight is like pretty big, then I may have like kind of go back and forth, and maybe I go to here, and then I remember that like my update will be the learning weight multiplied by the gradient, right? My gradient is this direction. Means my learning weight is pretty big, then I will go all the way outside this gap here, outside this hole here, right? This low point here. So therefore, like, but of course, like, when you do that, like sometimes you don't actually go down, but you maybe just go up to here. So when I increase learning weight from here to here, increase learning weight at this point here, I may actually just originally about in this region here, right? But when I increase my learning weight, I may go to here, something here. So then now I will at some higher loss rate. But then if I continue to move on, I may get out of this local minimum, and then I go down to another local minimum. So therefore I go down even lower than previously. Yeah, so.
Does Adam do that?
No, that's another paper. Yeah, you can, and of course you can combine all these always. Like you have Adam, and then you also do a cycle like this, and yeah, but I guess you can always just start with Adam and see like how it goes. I mean your training loss there, if it really going down, or like if it, yeah. But anyway, I guess we'll discuss more also like when how to babysit your training kind of like procedure there, yeah, later. So any other questions? So okay, I guess that's all. Yeah. I'll see you guys on Thursday.